Hello everybody, and welcome back to another video about the industrial automation. I'm very excited about today's topic because that's one of my favorite and I'm still learning about it, but I'm very excited to share whatever I know at the moment with you. Today's video about the redundant and high available CPUs from Siemens, which are S7-1515R and H. You're going to start from scratch, assuming you have no background in this topic. So I'm going to cover a few theory. Just bear with me, we're getting to the exciting part as well. And after we kind of learn a little bit about the redundancy, why we need it, why it's important, what is it overall, then we'll jump into the TIA portal, we'll create a new project, and then I'm going to show that how does it look like and how it works on real hardware which sits next to me. So without further ado, let's jump into the details. So in this section, we are going to have a very short theory about the redundancy and high availability and overall the importance of this topic in the industrial automation. So the first question that you might ask is, what is an RH CPU or controller overall? To answer that question, let's see how the traditional systems work or how the standard CPU and systems work. So as you can see in this slide, in a traditional way or in a standard way, we have a CPU or PLC sitting in a control cabinet somewhere in the plant, and several other components are connected to that CPU to transfer the information from the plant to the CPU or from sending the command from CPU to the actuator and some devices. So in this example, we have a single CPU and there we have a bus connection between some remote IOs that are sitting in the other side of the plant. But the problem with this architecture is if there is something goes wrong with the bus, let's say if there is any fault in this section, we will lose the communication with all other components in the plant, which is really not good. And as you may already guess, this is not a very efficient and optimized way to design a control system. So the first and the easiest solution to resolve this issue is using a ring topology instead of a line topology for connecting the distributed component throughout the plant to our main CPU. As you can see here, we have a ring. Let's say if there is any fault or if there is any problem in the connection at this point, we will not lose our connection to the distributed controllers and IOs because the connection can be established from the other side of the loop. Despite having a MRP ring to minimize the chance of error due to the connection problem throughout the network, there is still a big chance that we lose the CPU. So as you can see on this picture, if there is any problem in the CPU because we only have one CPU, the entire system will be shut down. So imagine what happens if there is any mission critical system under control, and definitely that's not good. So right now is the time to introduce you the redundant CPU or high available CPUs. As you can see on this diagram, in a redundant architecture, we don't rely merely on one CPU or controller to control the entire plant. In fact, we have two CPUs which work in parallel or at the same time to make sure if one CPU goes down, the other CPU takes over and controls the plant with the minimum interruption. So in this example, if we lose this CPU on the left side, we still have the CPU on the right side to run or control program or control logic to communicate with different components throughout the network. So I will explain further in the live demo section, but for now, just to let you know the way these redundant CPUs work, we have one primary CPU and one standby CPU. And there is an interconnection between these two CPUs, and if there is something goes wrong with the primary CPU, the backup CPU takes over and runs the program with minimum interruption. So in this example, as you can see, there is only Profinet line between these two CPUs, and that's how these two CPUs send messages to each other in case something goes wrong or when the faulty CPU is recovered. So we can still improve this architecture by utilizing the fast communication links such as the optical network to minimize the hiccup when one CPU fails and the other CPU takes over. So as you can see in this diagram, we have our MRP link And in addition, we also have these orange lines which represent the fiber optic connection between these two CPUs for faster interaction. So now that we know what is a redundant and high available CPU, let's see why we need it at all. So what are some real life examples for using your RNH system? So the first reason to use an RNH controller instead of a standard CPU is preventing data loss in the plant. For sure, if we lose the CPU, we lose everything. We don't capture any data, we don't control anything, and overall we lose a lot of valuable data that can cost us a lot of money. The second and one of the most important reasons for using an RNH controller instead of a standard controller is preventing plant downtime. As you know, in many industries, downtime is very expensive. Even shutting down the plant for a few minutes will cost hundreds of thousands or sometimes millions of dollars. The next reason for using an RNH controller instead of a standard controller is unmanned operation. That means we want to make sure if we install a system somewhere, maybe in a remote area that is not easily accessible to the operators, we want to make sure our CPU is rock solid and it will not go down easily. Another reason, which is kind of relevant to the previous reasons, is reducing the maintenance cost. So to make sure our system needs less maintenance, we can employ RH CPUs instead of the standard controllers. And last but not least, important reason for using RH CPUs is legal requirement. In many industries, using a RH CPU is a must, and you have to use the RH CPU, not just a standard CPU, because the system can be a mission critical systems, which I will give you some examples shortly. So let's just quickly review some real life example of RH systems. One of the interesting system is the airport baggage handling system. Definitely you've been in airport before and you hate having a delay for delivering your baggages, right? So the baggage handling system should be rock solid, and the engineer try to minimize the downtime as much as possible, and that's where an RH CPU can help a lot. Another real life example is railroad signaling system. Tunnels are another example for RH CPUs because the tunnel should always be under control, otherwise bad things might happen. Another example is a HVAC system or ventilation system in industrial or commercial system. Water and wastewater systems are another place where you can see RH systems, and overall RH system can be used in any system that needs a reliable operation, and those systems that should have a minimum downtime. You name it, in oil and gas, in mining, and many other industries that you can name more. So today's live demo will be on a Siemens redundant CPU. So let's learn some technical terms and some of the important specs for Siemens redundant and high available CPUs. So firstly, let's quickly see what is the difference between an redundant and a highly available controller. As you can see on this table, a redundant CPU, which is denoted by an R in the end of the CPU model, for example S7-1515R, consists of two CPUs which are coupled with Profinet connection. On the other hand, a high available CPU, which are noted by H in the end of the model, for example here 7-1500H, are coupled together by a fiber optic connection or H-Sync module. So as you can see from the table, overall the H CPU is faster and has more advantage over the R CPU. For example, one of the important factors is the switchover time. That means when the primary CPU goes down, the secondary or backup CPU takes over. In an H CPU, it only takes 50 milliseconds, while in the R CPU it takes 300 milliseconds. And both R and H systems support ET200SP and ET200MP and some other remote IOs offered by Siemens. And based on this application, you can select the architecture that matches your requirements. Another big difference between R and H CPUs is the distance between the primary and backup CPUs. And lastly, the maximum number of devices in the ring is recommended to be kept under 16 for R system and under 50 for H system. Alright, so let's quickly see how many redundant and high available CPUs Siemens has to offer. So overall, the main differences between these CPUs are, of course, the work memory, the amount of the program memory that you have, and then the speed of these CPUs, and the Profinet ports. If you are like me, you just want to see stuff, you want to see hands-on, so let's jump into the live demo. And this is the picture and this is the configuration that we are going to work on. We have a 1515R CPU, we have a network switch, and we have a 8200 SP remote IOs, and these are all linked together in an MRP link, and I'll show you in the TI portal how to configure this CPU and how easy it is to configure redundant CPU in Siemens world in just a few clicks in a few minutes. So without further ado, let's jump into the live demo. Here is what we are going to do in the next few minutes. So let's just add a redundant CPU to a blank TI portal project and see how to configure it and what's the process to configure a redundant CPU before downloading, and overall how the program looks like. And then we'll jump into the live demo and I'll show you how it actually works, and we'll trip the CPU and we'll simulate the fault to make sure it works. Okay, first thing I'm going to do in this blank project, I'm just going to project view, and then I'm just, as you can see, it's blank. So I'm just going to add a new device. In my example, I'm using a 1515R CPU, but if you're using another one, feel free to add that. So I just simply click OK. If you've done some PLC programming in the past, this window looks familiar to you. That's something that pops up whenever you add a new device or a new CPU. It's basically a wizard. You can just cancel it, or you can just go through the questionnaire. And here we're just going to give full access and hit finish. Okay, the first difference that you might notice in a redundant CPU is, unlike the traditional or standard CPU, which only adds one CPU to the project when you drag and drop it from the hardware catalog to your project tree, when you add a redundant or high available CPU to the project tree in TI portal, 2 CPUs will be added automatically. So if you expand the PLCs, you will notice something maybe strange if it's the first time you're working on redundant CPUs. One CPU looks exactly like a standalone and standard CPU. It has different folders in the project tree, such as program blocks, PLC tags, data type, traces, and so on, while the other CPU doesn't have anything. It really only has the device configuration and online diagnostic. The reason for that is, in a redundant system, we have a primary CPU and a backup CPU, and the project is executed in the primary CPU, and if there is something goes wrong with that CPU, everything will be transferred to the CPU backup CPU in a matter of milliseconds. But you don't need to write any single line of code to make that happen, because everything happens automatically behind the scene by these controllers. So all you really need to do after you're adding the CPU to the project is defining the IP address and setting a couple of important parameters. For sure, there are several parameters when you are implementing a real-life example, and based on your application needs, you have to define those parameters and fine-tune the controller and these parameters. So here, the first thing we want to do, we'll define an IP address for each Ethernet ports. Let's start with PLC1 or primary CPU. So the default IP address for X1 is 0.1. I normally leave that for my router, so I just change that to something else. And let's go to the CPU2 or PLC2 and do the same thing. So maybe I just use 202. Unlike a standard CPU, which only have one IP address, the redundant and high available CPUs have another IP address called system IP address. It is not enabled by default, but make sure you take advantage of this feature. So using this system IP address, you can connect other devices such as the HMI without the need to write any script to switch the server if one goes down and other takes over. In other words, you assume you are dealing with one single CPU, despite the fact that behind the scene these two CPUs are redundant and only one CPU work at a time. So you can define a system IP address and make sure both system IP addresses are the same, but as you might notice, When you define the system IP address in the CPU 1, it will automatically be populated on the CPU 2 as well. Okay, so after you define the IP addresses, one of the most important parameters that you need to take care of is under the advanced options, under the media redundancy. In the media redundancy role, you need to make sure these CPUs are managers. So as we mentioned, redundant systems are based on MRP ring. And in an MRP ring, you have a manager and also some client, which are other devices such as remote IOs. Okay, now that your CPUs have IP address and you have set up the required parameters, again, based on your project complexity, you might have to set up more parameters. Now you can come to the network view, or just right from the project tree, you can add other devices. For example, here, let's just add a remote IO. So I just drag and drop it here. All I need to do, I just drag and drop this port to my network, and I assign the IP address for that. And make sure you assign this IO device to the controller, and make sure under the advanced options, under media redundancy, you define this device to be a client. So we have a master or manager and also a client. So now you can just add your switch and other devices and basically create your loop in the TI portal. And once your hardware configuration is done, you can just jump into the PLC1 under the program blocks, OB1, and start writing your program. So at this point, programming is exactly like a standard CPU, and you don't need to write any script, you don't need to change anything in your program to make the redundancy happen, and everything is done automatically behind the scene by the CPU. Okay, now that you know how to create the project, how to add the device, let's just jump into the live demo and I'll show you the program, and then we'll switch the camera to see how the physical hardware looks like. Okay, so here we have a 1500 power supply, and we have a 1515R CPU, which are a coupled CPU, and also we have a XC208 network switch. We have an IM module, which is a IM155, which is a 8200 SP remote IO, and a few input and output cards. And as we saw in the TI portal in the network topology, these are connected as an MRP ring. You can see these two CPUs are connected together via this Profinet cable. So I'm not sure if the LCD is visible. Maybe I can just zoom in a little bit. Yes, I think it's much better now. So as you can see right now, they're both ready. And you have these icons on the display for primary and backup. If one goes down, it turns orange or red, and then you can see the rest. So let's just stop this, see the primary CPU, and see if there is any interruption in the rest of the IOs. Okay, so as you can see, the OB1 program is being executed and the digital outputs are switching on and off. And if we just switch the primary CPU off, or we just put it in the stop mode, as you can see, we don't see any interruption in the work of here. But if you pay more attention to the display, you will see that this CPU is stopped, the primary CPU is stopped, and the backup CPU is in the run mode. So if we just return the primary CPU into the start mode, you will notice after a few seconds, the primary CPU will take over again. Okay, as you can see right now, it's just copying the work memory to the other CPU. And the first CPU is also up and running. Okay, there you have it. Now you have the basic knowledge about the redundant CPUs, the importance of them in the industrial automation, and how to use them, and overall how you can configure and program one redundant CPU, which in our example we use the 1515R CPU offered by Siemens. The working principle for most of the redundant CPUs are the same from different manufacturers, but particularly in Siemens, it's very easy to configure a redundant CPU, and everything is being done automatically for you behind the scene, and all you need to do is really just setting up the IP address of the CPUs and doing some small configuration and fine-tuning. I hope you found this video useful. I tried my best to cover everything that you need to get started, But definitely there are more questions, and I'll be more than happy to answer that. And don't forget to reach out to your local Siemens representative and ask for the expert on the redundant system if you are designing a redundant system based on the Siemens platform, to make sure you get the most of your investment, which is the hardware and the software that you bought for your project. Okay, until the next time, have a great day or night.